email. We have one case in our institute where we might have a corona case. Hopefully it's not true, so we will find this out this afternoon, because the PhD student was tested with a PCR test, so then we know exactly what's going on. But just in case, we wanted to be a little bit careful, and therefore we decided to go online with this lecture today. Hopefully we can be in present next week again. But to be sure, I thought it's a good opportunity to do it like this. And as you know, you're always sitting very close in the room in our building O, and therefore even for this reason, maybe it's better to go online. Okay. Any comment on that so far, or questions, how it works? So I guess it should be no problem for you to follow. And by the way, I can also record the lecture if you want to. This is one of the advantages if we have the online lectures, that I can record them. Let's see. Look. Oh, I can't record this lecture. I don't know why, but it seems not to be possible. Okay, sorry for that. But as I can see from the participants, it seems that everybody of you has the opportunity to watch this online. Okay, so as you can see further on, I changed the order of the lectures a little bit, because usually today we would talk about these design and scale-up of reactors, but this is something that works much, much better on the board. And therefore I decided to switch today to this process with phase changes. This is also very convenient to give this lecture online, and therefore I switched these two lectures. I hope this is fine for you. Okay, so boiling and evaporation, these are two very important heat transfer processes, as you probably know. And today I would like to introduce these two kinds of process more in details. And of course, once again, we will see some correlations that helps us to calculate the heat transfer performance in case of evaporation and boiling and condensation. You might remember we already talked about these very much higher heat transfer performance in the case of phase change. But today we will see more in detail what is the reason for that, why phase change so strongly enhances heat and mass transfer. So therefore, let's talk about the topic. So these are the contents. So we will talk, have a brief introduction. Then we'll talk about pool boiling, nuclear boiling, flow boiling, film condensation, and we finish the lecture today with a very brief introduction into heat pipes. Okay, everything's okay for you so far? Okay, there seems to nothing against that. Otherwise, of course, you can also use the chat if you have questions, or if you have questions or want to make some comments, and please use the microphone, switch just your microphone on. If you want to, then you can switch on the camera, but you can also use the chat however you want. And I have all this, I see all these informations here, and then we can hopefully also have some discussions if you have questions in between. Okay, so here you see a very typical example of boiling, and you all know this from your home. If you are cooking water, if you're cooking your eggs on Sunday morning, then you probably will have this kind of cooking water situation here, or if you prepare your tea. And these are, of course, special bubbles that you see here. These are steam bubbles. Steam is appearing here from the bottom, and then the steam bubble is increasing, and we have here a strong mixing by this buoyancy-driven flow, buoyancy driven by the gas, by the steam bubbles. And of course, this also enhances a heat transfer in the whole situation. But how can we describe these boiling process more in detail? So first of all, for the introduction, of course, it's very important to know more about boiling processes, because in industry, usually these evaporation and condensation is used for heat transfer very, very often. And the reason is that if we have only heat transfer without any phase change, then we only have the heat capacity of the fluid that can be used to transfer the heat, only by the heat capacity of the fluid. If we use evaporation or condensation, then we have additionally to this capacity, heat capacity of the fluid, we have the enthalpy, the evaporation and condensation enthalpy for the fluid. As you know, the enthalpy is much, much higher than just the heat capacitance. And therefore, this is a big reason why, for example, in power plants, here we see, by the way, in a nuclear power plant, why condensation and evaporation is used. So here we have the very high heat of the nuclear reactor, and this strong heat is transferred by steam. So here you see these are steam lines into the generator, and so we evaporate here water in the nuclear reactor. And the evaporated steam is here transferred to the generator to produce the current. And afterwards, here with this condensator, the steam is condensated again, and then the condensated, so the water, let's say, is transferred here again to the evaporators. Yeah, so the evaporation and the condensation, this is the biggest step here for transferring the heat in this case. And of course, we don't have to talk about nuclear power plants. In our days, it's much better to talk about renewable energies. But even for renewable energies, here you see this solar tower in Almeria in Spain at the Plataforma Solar, where sunlight is bundled here on this very, very hot spot. And in this hot spot here, we have a evaporation of water as well. Yeah, so it's the same system, the same idea. But here the heat comes from very bad nuclear power, and here the heat comes from very climate and human-friendly solar energy. But in both cases, you need to know as engineers how to evaporate and to condensate, and how much energy and heat can be transferred with this condensation and evaporation. So it's really worth to talk about that. And furthermore, we have also these phase change, condensation and evaporation. If we talk about the concentration of products, think about food industry, where we have milk powder, for example, or coffee powder. Both is usually first in a liquid phase, and then by drying and evaporating the liquid phase, we come to dry powder. So this is a phase change that we have here. Also, if we dry in food industry, cacao powder, for example, this is an evaporation process. And these are typical applications in industry. And we already talked about the latent heat for evaporation and condensation that we use in power plants. It's used for air conditioning and refrigeration in heat pumps, for example. Power plants we talked about. Yeah, and these are the very important, some examples of very important processes where the latent heat and evaporation and condensation comes into play. So this means, in other words, that this boiling, the liquid phase, is a very, very powerful process to enhance heat transfer. We will see in a minute why this is the case. But unfortunately, this is also extremely dangerous to produce so much heat that water is boiling. And of course, it's not so dangerous on your stove in your kitchen, but in industrial processes, it can be extremely dangerous. And this, by the way, is the reason why a lot of money has been spent to research of boiling in nuclear power plants, because it's so dangerous. And I will try to explain you why this is so dangerous. And therefore, this is a very, very important lecture for your professional career. And I hope that you never forget this what I will tell you in the next 30 minutes. So it's very nice to understand with this very simple experiment, and this is the experiment that has been derived by Nukiyama. So it's a Japanese researcher who derived this nice experiment, and it's a very simple experiment. So we have a water basin here, and in this water basin, we have a thermometer to measure the temperature. So we can measure the saturation temperature here. And we have two metal bars here, and they are connected with a wire, with a metal wire. And now we can measure in between these two metal bars here, in between these two sticks, the current. And we can also get the power here, the potential in between these two wires. And the potential, in Germany we call this U, yeah, this is die Spannung, U, this is the potential, this is the current, here is der Stromfluss. And as you probably remember from your electronic studies, we can calculate the resistance of the system, of this wire, by dividing U by E, yeah, URI. This is the law, URI in German, yeah, you probably remember that. This is a law to calculate the resistance of the wire by dividing the potential by the current. And as you probably know as well, the resistance of a wire depends on the temperature. The higher the temperature, the higher the resistance of the wire. In other words, by calculating or by measuring the potential and the current here, you can directly come to the temperature of the wire if you have this calibration curve. So here we have measured the temperature, and we saw that with increasing temperature, the resistance increases, and therefore we can use this as a calibration curve, and by just measuring current and power, we can calculate the temperature of the wire. Very nice. And there's another nice point, and this is that we can directly also calculate the heat transfer power that we spend to the water, and the power of heat transfer is nothing else than the current multiplied by the potential. You might remember, yeah. Here we have E multiplied by I, so the potential multiplied by the current. U mal I is P, as you probably remember from your German courses. So E multiplied by I is capital Q, and if we divide this by the area of the wire, then we come to the area specific power, and this is nothing else as Q, as our heat that is transferred. So this is a very, very nice and elegant experiment, because with just two measuring values, current and power, or on the other hand, let's say, of course, usually you use here constant potential, like 20 volts or 220 volts, probably not, maybe 20 volts. And then you're measuring only the current. And just by measuring the current with a known potential, you can get the temperature of the wire, and you can get the heat that is transferred. Very, very simple and elegant experiment. Okay, and by doing that, we have now the opportunity to look how much heat is transferred if we increase the current. If we increase the current, we increase the temperature, and with increasing temperature, we will create more heat transfer and more evaporation of water. And so we can measure and can see what happens if we increase the heat. And if you do that, then you will see that you get different situations of evaporation of water at the wire. So first of all, we have a good contact between water and between the water and the wire. And so if we increase the current, then the first bubbles will appear due to these boiling, and this is called nuclear boiling. Nuclear boiling is that some tiny bubbles appear here, and this is when the boiling starts. This is nuclear boiling, and in that case, first region, we have isolated bubbles that are rising here from this wire upwards. So, and as Q and delta T increase, more and more sites are activated. I guess this is easy to understand. If we have a higher current, then more heat is transferred, and then we get more boiling situations here, more bubbling sites. So if we increase the current further, then we will transfer even more heat into the water, and this means that more and more vapor bubbles are appearing here. And this brings us to the second region of slugs and columns. Yeah, here, when the active sites become very numerous, the bubble starts to merge into another bubble formed, vapor formed at the surface, merged immediately into jets that feed into large overhead bubbles or slug vapor. And here we have this slug formation, big areas where only vapor appears in the water phase. So here we can see another picture. So the isolated bubble regime, here we have the plug regimes. By the way, you can do this in water, and you can do this also in some solvents. Here, for example, we see this for acetone, and it's the same situation. So with this nice experiment, you can do this as well for different systems. And if you increase further the current, then we come to these regimes of slugs and columns here. And then suddenly, if you increase the current further to higher heat transfer performances, then suddenly you get, once again, these very nice situation here, these very nice, well-ordered bubble formation. And this is strange, isn't it? So we increase the heat even further, and despite the fact we increase the heat, we come from this totally chaotic regime where a lot of steam is formed at the wire to this very well defined situation where only a little bit of steam is formed at the wire. And what is the reason for that? This is, on the first view, very astonishing, but this is a regime of film boiling. And if you have film boiling, what happens is that you have so much vapor that appears here at the wire that the vapor cannot escape anymore by vapor bubbles. So in other words, you get a vapor, a very, very thin layer of vapor around this wire, and this very thin layer of vapor acts like an isolator, because as you know, the heat conduction of liquid, of water, is much, much higher than the heat conduction of vapor. So in other words, this vapor layer here acts like an isolator. And this means that despite the very, very high temperature of the wire, not so much heat is transferred across these vapor layer, and therefore only less bubbles are created by evaporation, because the heat transfer is limited by the conduction in the vapor layer. Okay. Yeah, do you get this? This is very, very important basis for what we discuss in the following. So despite the fact you increase the heat transfer performance or the heat, the transferred heat, but actually, of course, you don't increase the transferred heat because it's limited by this vapor layer. Maybe we look on this diagram. This is a very, very important diagram, and you can be sure that I will ask you this in the examen, because it's so important that you know that after these lectures. So this is an extremely important diagram that explains this situation. What happens? So here you can see the wall superheat on the lower axis. Wall superheat means this is the wall temperature here, TW, and this is a saturation concentration in the liquid phase. In other words, this is a temperature where the liquid starts to evaporate. Yeah, so wall temperature and temperature where the liquid starts to evaporate. And this is, of course, the superheat of the wall, because the wall temperature is higher than the saturation concentration, saturation temperature. In other words, vapor bubbles will appear here, of course, because we are superheated. On the other hand, on this axis, we have the heat flux. So here you see the Q, and it's given here in non-logarithmic scale. So the lower axis is logarithmic, the upper one is not logarithmic, so half logarithmic diagram. And here we have 10 to the power of 5 watt per square meter. Yeah, do you remember if we multiply the current with a potential, U multiplied by E is then we have our power in watt, and we divide by the area of the wire. This gives us square meter. So watt per square meter. So now let's have a look on this diagram. What happens if we increase the wall superheat? So if we increase the current to increase the heat flux, what happens? And first of all, we have here a low heat flux, of course, yeah, because it's not such a high temperature that we have in our wire. If we increase now the temperature further, then of course the heat flux will increase. Yeah, this is not very surprising. This is only natural convection that takes place here. After a wall superheat of about 4 degrees Celsius, the first boiling starts, yeah, because the heat cannot be transferred away anymore only by natural convection, so that an additional phase change happens. So here we feed so much energy into the liquid that we overcome the lateral heat, and therefore evaporation starts and we get the first boiling. And now something interesting happens. If the first bubbles appear, we get a much steeper increase in the heat transfer performance, as you can see here. Yeah, we just, here for the first 4 degrees Celsius superheat, we have only a little increase in heat transfer performance. If we increase the superheat here by 6 degrees Celsius more, we have a tremendous increase in our heat flux, and this even gets much, much stronger with higher superheating the surface. So here we have a very, very high increase in the heat flux. So, and this entire range here is called this nuclear boiling regime. Here we have isolated bubbles. So this was the first regime. This is a regime that looks like this. And here we have the region of jets and columns. So this is a region that looks like this here. Yeah. And why is the heat transfer so strongly increased here? Yeah, the reason is, of course, that as you can imagine, we talked a lot about turbulence. So the stronger the turbulence here, the stronger is the, let's say, refreshment of the surface by fresh liquid that is pushed to the wire by the turbulences, by the rising and separating bubbles. And so this means that we have a much, much better heat transfer performance here. Of course, don't forget this is a logarithmic scale here. So in other words, these are 90 degrees Celsius. Here we have only 9 and these are 90. So of course we have also a much higher temperature difference that additionally increases the heat flux, but also the strong evaporation and bubbling on the surface and the change of surface enhances these heat flux here. So now something interesting happens, and something unfortunately extremely dangerous happens, because if you are at this point here, then you will say, oh, wonderful, we just increase the heat flux and the superheat, and this increases the heat flux. So we can try to go here to superheat of 200 or 300 or 400 degrees Celsius, and we will get a tremendous high heat that is being transferred. But unfortunately, at a certain point here, suddenly, and really suddenly, and this is a dangerous situation, suddenly the heat flux breaks down. And this is exactly the point where this situation here appears, where we feed so much heat into the system that the bubbles cannot be disappear fast enough, so they cannot separate fast enough to transfer all the heat away from the wire. And this means that we get a vapor layer around the wire. We get a tiny vapor layer, and that is what happens here. And here we have now suddenly this isolation situation due to the vapor layer. And this isolation situation means that now the heat flux dramatically breaks down to a very low heat flux here. Yeah, you can see here we have 12 watt per square meter, very strong heat flux. in these bubbly and jet regime. And now we get this vapor film and the heat flux breaks down. And this is extremely dangerous, because in the same time the heat flux breaks down, if you look to the temperature and we have this logarithmic scale, you'll see that suddenly the wall superheat increases as well dramatically. And this is a dangerous situation, because very often we use these evaporation and in cooling systems for chemical processes, or think about the nuclear power plant. And of course, it's extremely dangerous if suddenly the heat transfer performance breaks down and the temperature of the wall gets so hot like this, because it happens very fastly then that if you have a constant heat source like a nuclear system, that then the temperature gets so high that the metal is melting. And then, of course, you are in big trouble. If the metal of your heat exchanger is melting, then you don't have any cooling performance anymore, of course. So first it breaks down, and then then the whole system might break if you not take care about these critical point here. Yeah, so very, very important critical point. So there is a maximum heat flux that can be transferred, and after that, heat transfer performance breaks down and the temperature suddenly increases very, very strongly. Yeah, and this is a dangerous situation. This is called peak heat flux or burnout point or boiling crisis. There are several expressions for that. All expressions show that they're having something that is not very, very welcome. And here I have written down this once again in my own words, and also in the words from Lienhard. And I really would like to motivate you to read this once again and to study this very much in detail and to understand very much in detail what's going on here, because it's a very, very important situation, and every engineer, every process engineer at least should know this, should know about the burnout point and these boiling crises. Yeah, so please have this in mind, what can happen if you try to enhance the heat flux too much by using evaporation processes. So here once again, we have the transitional regime and we have the film boiling regime, but I have now explained you all these different situations. Here is another diagram that shows what's going on here. We have the temperature difference between wall and saturation temperature. We first have a strong increase in heat flux by this bubbling regime, and then suddenly it drops. There's one question in the chat: why does it increase again after breaking off? Very good. Thank you so much for reminding me that I have to explain that. Does anybody has an idea what's going on here? It's a very good question. Why is the temperature or the heat flux increasing here once again?
Well, I would guess it is because the air or the gas, the vapor, also transfers some heat. And of course, it also transfers more heat as the temperature gradient increases. And at some point, we would also have a big heat transfer, but that is just by vapor, probably.
Yeah, so you mentioned it's conduction, right? Conduction through the vapor film, because in the film there is almost no strong convection, so more or less conduction. Yeah, thank you. This is true. For example, we still have some heat transfer, and don't forget this is a logarithmic scale. So you can see here we are at 1000 degrees Celsius temperature difference between the wall and the saturation concentration. And then, of course, we have this situation, but there's something else that comes into play here, and this is heat transfer by radiation. Yeah, we'll talk about that later on in the lectures as well, about heat transfer by radiation, and here radiation comes into play. And as you might know, radiation don't need any fluid to be transferred. Radiation don't need any convection or conduction. Think about our heat that we get from the sun. it goes through the vacuum in space, and even there's vacuum, there's no opportunity for conduction and convection of the heat from the sun. And despite the fact we have very nice warmy summer days here, and this is only due to radiation. But as mentioned again, we will talk about that a little bit later on. And someone mentioned film is removed. Yeah, no, unfortunately not. The film gets thicker and thicker if you increase the overheat, the superheat. But yeah, as mentioned again, it's conduction and also radiation that comes into play here. But thanks you so much for the nice question. I forgot to mention that. There's one other question. So in industry power plant, we want to stay in nucleation, right, by adjusting area. Yeah, thank you for this hint. This is also an important point. I go back. Yeah, it's a very good point. So what will you do as engineer? So probably you will try to use this area here where you have very good heat transfer performance, but it's very important to stay away from this critical point. So probably you will go here to a heat flux of, let's say, 8 or 10 watts per square meter, but not higher, to be sure that not due to a terrible, yeah, just by chance you overcome this point. And this can happen very fastly. I think about, and you have some scaling in the heat exchanger, or a very short heat flux peak or something like that, and then you overcome this point. And if you overcome this point, then you will never come back, yeah, because you have suddenly such a strong increase in the temperature, you will not have any chance to come back here. The only chance is to switch off your heating system. But as you know, in nuclear power plants, this is not so easy, as you unfortunately have learned from the Chernobyl accident. Yeah, so please be careful and keep away from this very dangerous and critical point here, not to go to too high heat fluxes. And of course, this depends on the material system. Yeah, so this is for water. If you have other materials, then you have to think about that and have to do some calculations again. Okay, so what's going on now? If we look on the microscopic view on our situation, what's going on? Why do we have this strong increase in the heat transfer performance, and how are the bubbles formed on our surfaces? And therefore, I would like to show you this graphics here from the book of Lienhard that very nicely shows what's going on. The point is that we have to overcome the Laplace pressure. Yeah, you might remember we talked already about the Laplace equation. The Laplace equation was a pressure difference in the bubble and at the ambient condition. So this is our pressure difference. And we have the radius of the bubble. This is here these RB. This is the radius of the vapor bubble. And here we have 2 multiplied by the surface tension. Yeah, we had the equation before a little bit in another arrangement. We had here delta P is 2 sigma divided by R, you might remember. But now we are interested in RB, because this is the diameter, this is the size of our vapor bubble. And now let's see what's going on. This means that the surface tension is more or less constant for our vapor bubble. But this means if the saturation concentration here gets higher, yeah, by increasing the temperature, so the superheat, then ambient P is constant. If we increase this difference here, then the radius increases. So in other words, we have to overcome a certain pressure difference to blow up this vapor bubble. Yeah, you know, if you have a balloon, and if you push your air into a balloon, if the balloon is very tiny, then you need a lot of force, you need a lot of pressure to pump up this balloon. If the balloon has a certain size, then it's much easier to expand the balloon even further. This is a model example what's going on here. The more tiny the bubble is, the more pressure you need to blow the bubble up. And this, on the other hand, gives us a very interesting phenomena, because this means that bubbles will appear at a point where we already have a certain radius. Because if we have somewhere a certain radius, then the temperature pressure difference, and therefore the temperature difference we need to pump up this gas bubble or this vapor bubble, is much lower. And this is the reason why vapor bubbles always appear at points on your surface that are a little bit curved. So we usually have a certain roughness of our surface. Here's the roughness of our the bottom of the pot where we are cooking our water. And if we look in detail into this roughness, and it looks like that. And here, for example, we might have a very tiny gap where some gas is already included. And this means if we now feed heat into the system, then here at this point, we already have a radius of a certain size. So it's much easier for the vapor to be created here to create more interface because we already have this radius. And this is why we have these nucleation sites here. Here's the nucleation site. Here's the nucleation site. Everywhere where we already have some gas inside and where we have already a radius of a certain dimension, we will create more and more vapor and pump up these vapor bubbles. Okay. And I very much recommend you next Sunday, if you're cooking your eggs on your stove, please look on the bottom and observe what's going on there in your pot. And if you observe that, then you will indeed see that there are only special sites, and usually these are some scratches on the bottom of your pot. These are special sites where the vapor bubbles appearing for the first time. And at the beginning, of course, they are very, very tiny, these bubbles. Then you have this typical nuclear boiling. And then if you wait for a longer time and the water gets hotter and hotter, then you will see that you come to these jet regimes and column regimes of the vapor bubbles. Probably you will never cook eggs again without thinking about this phenomena. It's quite interesting to observe if you do that. So what does it mean if the bubble is growing and if the bubble is detaching? So here we have a drawing that shows our bubble that has now already created. And at a certain point, the buoyancy of the bubble is so large that the buoyancy force is stronger than the surface tension force. It tries to keep the bubble back. And at this moment, the bubble will lift off here and will rise into your continuous phase, into the liquid phase. And what now happens is that if the bubble is rising, then of course we depleting some liquid here, and then water flows back from the back below the bubble here. And this, of course, causes an additional convection. And this is a strong additional convection that, of course, also increases the heat transfer performance. Yeah, there's one question from Lawrence Heinz, please.
I had a question. So about the roughness of our pipe, let's say from our heat exchanger, do we have a certain prescription what roughness we would ideally want for a heat exchanger, or would we just say it doesn't make a difference at the end of the day?
Very good question. It's important for this nucleation. But usually in the heat exchanger, if you don't want to evaporate, then the roughness is more important for the friction and for the pressure drop of the pipes of the system, but not so important for heat transfer. Here we only talk about evaporation. And if you want to evaporate, then it makes definitely sense to think about a well-defined evaporating surface. So usually in large apparatuses, as far as I know, this has not been taken into account because they are just using steel and all other questions about the price of the steel and and how resistant the steel is. All these points are more important than the nucleation sites. But I know that this is a very big topic in micro heat exchangers, because micro heat exchangers, there you are fighting for every watt per square meter that can be transferred. And there are some interesting papers that looked on different topologies of the surfaces and shapes to increase the heat transfer as strong as possible.
Oh, interesting. Thank you.
Yeah, you're welcome. And there's another question. Are these sites also the cause of fouling? Yeah, you're right. This, of course, is another point. Very good comment. Thank you for that. Depending on the process, if you have a very pure process, like in the pharmaceutical industry, then of course you will avoid these kind of scratches, because otherwise you will get contaminations here. Yeah, and it's difficult to clean this up again after process. So very good hint. This is also often a question. Okay, so this means, as I have mentioned, the detaching vapor bubble here influences the flow around it. So we get strong convection, and this convection enhances the heat transfer even further. And sometimes, and this is also interesting, you can also observe this in your pot if you're cooking your eggs. Then what happens is, at the beginning, if the water is too cold outside, then the vapor bubble will rise up, and due to the cold water above the bubble will condensate again. So you will see that bubbles are appearing at the ground, they are rising upwards, and suddenly they're disappearing again. And sometimes they're disappearing again as well here at the ground, because of directly evaporation and condensation, because the liquid in the surrounding of the bubble is too cold. This is another important and interesting effect. Okay, and now I would like to focus on another phenomena here with this slide. And I very, very much regret that I'm not in the lecture room now in front of you, because I like very much to explain this very, like an actor, because it's a very important phenomena as well. And you really should know that. And I hope that I can bring this to you even online. As I have now explained, we have these nucleation sites where the vapor bubbles are created. I ask you, what happens, and this is very, very nicely related to your question that you just have with this very smooth surface. What happens if we don't have this critical radius here, RB? What happens if we have a very, very flat and a very, very smooth surface? What happens in that case if you increase the superheat?
Is it that the bubbles, it's harder to form the bubbles and the temperature keeps rising?
Exactly. You're right. And then, and what is the problem? Why is this so dangerous?
I think maybe the vapor film forms. Okay.
Yeah, usually it does not happen in larger scale. But what happens, people, so chemists and biologists are very afraid of that phenomena in the laboratory, because if you think about a glass, a glass system where we have, for example, distilled water inside, so very pure water, and to put this on the stove, and you have a very flat glass surface. What happens, and you're totally right with that, so due to the missing nucleation sites, the temperature increases and increases and increases. So we have a supersaturation temperature of, let's say, 10 to 20 degrees Celsius. So it's quite strange. You can measure the temperature in your pot, and the temperature will be at 120 degrees Celsius. And despite you have 120 degree, you still have no cooking. So everybody is telling you that water cooks at 100 degree, but without any nucleation site, you will not have this cooking. And now let's see, there is one comment in the chat: with increase in temperature at the bottom, the density reduces, whereas the temperature at the top is lower, thus the liquid is higher density. Bulk convection, yeah, that's true. We will get bulk convection, but bulk convection we will get anyway. Yeah, so as soon as we have temperature gradients, we get some bulk convection in the system. But this is a more dangerous phenomena I just mentioned, because now you have a temperature that is, let's say, 10 or 20 degrees above the cooking temperature. And now you can imagine what happens if you now disturb the system. Let's say you push one tiny grain into your water that has 120 degrees and is not cooking. Maybe you can imagine what happens. At this point, you have suddenly these
expansion.
Exactly. Yeah. Then you get a terrible expansion, because now you have a radius with this tiny grain in your system. And sorry, I hate this. And at this tiny radius, the water will start to cook, because here you have the nucleation site where the first bubble can be created. And if you have one bubble that is created, then you get a lot of more tiny bubbles, and then more and more nucleation sites appear. And so you will get a very, very rapid overcooking of your system. So it's like an explosion. Suddenly the whole water shoots out of your system with a temperature of 120 degrees. And you can imagine this is really, really dangerous in laboratory, and you really should be aware of that, and you should definitely warn your staff, your laboratory staff, not to do that. But how can you avoid that? There's a very simple way to avoid that. Does anybody know that? I know we have some people in our lecture who already have an education in chemistry and biochemistry. Do you remember?
I believe that there are some stones that you can just put into the water to act as nucleation sites.
Exactly. This is a solution. You can put in some stones. They are called nucleation site stones, or in Germany we say Siedesteine. Yeah, Siedestein. And these are stones, and these are really nothing else than simple stones. And these stones have this grafts here to create the first nucleation sites for the cooking. So you put something into your water where the cooking process can start, to avoid that you get this dangerous overcooking process. Okay. Good. So that is what I wanted to give you as a take-home message, because it's such an important phenomena, and it nicely is related here to our lecture today. So therefore I wanted to give you this information. So please be careful about the nuclear boiling and these, and take care of that your laboratory staff will always use these stones as nucleation sites. So now we can have a look on how this cooking process works, and therefore we have this graphic here. You see, but this we know this already. This is a specific volume here. This is a pressure, and this just shows us that we get certain sizes of the bubbles if we overcome a certain pressure. Yeah, here we have the super temperature. This is here our pressure, our ambient pressure, and now you can see if we increase, if we overcome these critical pressure, then the bubble will create it. And this temperature difference here is this is a superheated temperature, and this is the pressure difference that is related to our surface tension and the bubble radius. So this is how it is created. And with this, we can calculate our saturation temperature and the temperature in the system and the surface tension that appears here. So we can calculate surface tension, and with the surface tension and the temperature difference, we can calculate the radius of the bubble. This works with this diagram, and of course, we need to know the surface tension for this Laplace equation here, And the surface tension, you will find this in several textbooks here. In Lienhardt, once again, it's given for different systems like mercury, methane, alcohol, and this is the equation. And you see with these two constants, A and B, with these two parameters, here's A and B given, you can calculate the surface tension independency of the temperature. This is a nice empirical correlation to calculate surface tension independency of the temperature. Okay, any further question related to this topic? Okay, now you know how bubbling appears. Here I have some other little bit older slides, but they are showing, that are showing the same situation. We have the vapor bubble that appears over the heating plate. Then we have a certain break of diameter here of this bubble. And if we overcome this break of diameter, then the buoyancy force gets larger than the surface tension force, and then the bubble lifts off. And we get here a sub-pressure region in the wake of the vapor bubble, and with that we get some convection here from the surrounding. And now we can, of course, make a force balance between the surface tension force that keeps the bubble back and the buoyancy force that is introduced here by the lower density of the bubble. And you might remember we talked already about bubble formation at orifices, and this is very similar here. So with this equilibrium, we can calculate the critical diameter of the vapor bubble. So at this critical diameter, the bubble will lift off. And here we have a correction factor, these beta 0, surface tension, gravity, and of course the density difference between vapor bubble and the surrounding liquid. So this is a so-called break-off radius of Metro Voc, who has created that. Yeah, and now due to these effect that the bubbles are leaving the surface, we know that we have higher heat transfer coefficients. Yeah, so the heat transfer coefficient, watt per square meter Kelvin, the heat transfer coefficient, of course, increases because we have this much higher convection at the surface if we have the lift off of the bubbles. And this heat transfer coefficient depends on the material system we have. And therefore, you can see here in this diagram, this is the heat flux. Of course, the higher the heat flux, the more vapor bubbles are created and the more refreshment of the surface and of the boundary layer, the liquid boundary layer we have. So therefore, it's not very surprising that with increasing heat flux, also the heat transfer coefficient increases. Yeah, due to the stronger convection if the bubbles are leaving the surface. And you see here we have propane, ammonia, freon, water. You have water at 1 bar. By the way, these freon here at 5.3 bars and 11 bars, freon, as you might remember, it's forbidden right now. It's a little bit older diagram here from a former colleague. And these freon is a cooling liquid that is usually used in refrigerators, or let's say it has been used in refrigerators before it was forbidden. And you can see here the higher the pressure, the lower is the alpha value, because with higher pressure you get smaller vapor bubbles, of course, yeah, due to the higher pressure. And the smaller vapor bubbles mean that we have also less convection in this case. Yeah, so this is why the pressure is taken into account, and these are typical pressures of these refrigerators or air conditioning systems. And for that, a lot of research has been done, because in refrigerators and air conditioning systems, you can imagine evaporation and condensation plays a very, very important role, so that you need to be able to calculate the heat transfer performances. So, but of course, we would like to calculate the heat transfer performance. And how can we do that? How can we calculate the heat transfer performance for condensation and evaporation? And for that, we look on our well-known equation that we use in all the way. If we want to calculate heat transfer performance, we use our dimensionless Nusselt number. Yeah, and you already know this shape of our Nusselt number correlation. We have a factor. We have the Reynolds number that takes into account the convection to the power of x, and we have the Prandtl number that takes into account the material properties, so conductivity and the heat, the thermal conductivity to the power of y. So Reynolds multiplied by Prandtl with two exponents and a factor. This is an equation that helps us to describe the heat transfer performance. So now we can try to get this a little bit more in detail, because we know already that the Reynolds number here depends on our nucleation at the pool boiling situation. So therefore, we can exchange this Reynolds number by the equation we saw before that takes into account here these situation, the buoyancy force. And further on, of course, we need our heat transfer coefficient for nuclear pool boiling. So this is, once again, our alpha value, but it's the alpha value for the nuclear pool boiling. So we use KL, this is a lambda, this is our alpha, and this is our characteristic length in this case, the characteristic length that comes from our length that is induced by the separation radius. Let's have a look back to this. Yeah, here you see square root of 2 sigma divided by g and the density difference. This was a break-off diameter of the vapor bubble. So this is a characteristic length here that we find for pool boiling, and so we can use this diameter. So we don't need this and the beta, because this can be taken into account in any other coefficient. But what we need are these physical background here of the critical diameter. So we introduce this critical diameter here. Yeah, you see sigma divided by g, density difference, square root. We use this as critical diameter. Yeah, and because we use here adaptation factors with this alpha anyway, we can put these two correction factors here also into our alpha, because we will estimate and measure this alpha anyway. So this is our equation for the pool boiling situation. And now we need another equation for the Reynolds number. And for the Reynolds number, we have defined the Reynolds number with this equation here. Here we have the characteristic length, once again our critical diameter, and then we exchanged the velocity in the Reynolds number with a heat flux q here, because this is related to the flow velocity, and we divide this by the latent heat for evaporation, and the density is taken into account here twice to use here the viscosity of the liquid phase. So this is our Reynolds number, and you can try to set in here the units, and you will see this is dimensionless how it should look like. But this is our Nusselt number for nuclear boiling. Yeah, and now we can bring this together. We can come back to this equation, and we will see that we will find in literature a correlation that uses this correlation, and this is a so-called Rosenau correlation. And the Rosenau correlation looks like this. So you see here all the parameters we have just described. Here's the Reynolds number, yeah, Reynolds to the power of n, and here's the Prandtl number, Prandtl to the power of m. Here we use m plus 1. Don't ask me why, because the reason is that we can use then these parameters here for water M is 0, so we have just the Prandtl number for water here, the simple Prandtl number. For other fluids, the Prandtl number has to be adapted due to the different material properties. Then M is 0.7. And N in both cases here is 0.33. And the big achievement of Rosenhoff was that he introduced additionally a surface correction factor, because we have just seen that the surface and the roughness of the surface plays a very important role for the nucleation process. And therefore, even for the heat transfer, this nucleation process is important, and the surface roughness, the surface correction factor is important. Yeah, and here we have the Nusselt number once again. Yeah, so this is our Rosenau equation, and this equation pointed out the importance of the microtopology of the boiling surface or nuclide boiling already. So here we can see how this equation works. Here we have the heat flux. Here we have our supersaturation temperature in combination with heat capacity and Prandtl number and the latent heat. And you see that we get almost in this double logarithmic diagram here a line. And this line here, we have the equation, the Rosenau equation. And you see this line very nicely fits different material systems. So here we have different pressures, and we have very different material systems, water nickel for the surface, fluid combination, water platinum, ethyl alcohol chromium, isopropyl alcohol copper. You see we have many different materials here for the surface and for the liquid phase. And we can only choose different surface correction factors. And we come to this good agreement between heat flux and supersaturation. Okay. So this is our equation to predict heat transfer performance in boiling processes for different liquids and surfaces. Here's another example, and you see this is from a not very old publication from 2004. And from this publication from 2004, you see this is still very actual, this topic, and it's still very, very important to know how to correlate the heat transfer performance. So this is given here with H. Don't be confused. H is here the heat transfer coefficient. Yeah. So sometimes it's a little bit strange what kind of characters are used. Here, H is used for the heat transfer coefficient in this literature. So you see this from the unit kilowatt per Kelvin and square meter, and you see how nicely these Rosenau correlation fits the experimental results for these four very typical refrigerants that have been used here. Yeah, and here you see the different refrigerants, and plus minus 20%. We have a very correct prediction estimation of the heat transfer performance here between the correlation and the experimentally measured heat transfer performance. So very nice evaluation of the Rosenau correlation through experimental pool boiling of halocarbon refrigerants on cylindrical surfaces. Journal of Brazilian Society of Mechanical Sciences and Engineering. You see actual paper that still deals with this important topic. Okay, so now let's go to a more realistic case, because all this has been derived only at flat surfaces. Usually we have pipes where we're interested in. And what happens if we have a pipe? And now let's have a look on the evaporation in the pipe. And you already have seen this picture several times. Here we have a vertical pipe, and we feed now the heat into this pipe. Let's say this might be a heat exchanger pipe for a vertical arranged heat exchanger. We have maybe very hot gas at the outside, and we will cool this gaseous phase. So heat is transferred into the pipe, and then you will agree with me. First, we have only the water phase, And with increasing heat that is transferred, more and more water will disappear. So in vapor will evaporate. First, we have here these nuclear boiling. We get slugs, we get film, and at a certain point, we only have tiny bubbles, tiny droplets. So we come from bubbly flow here to the plug flow regime. We come to the annular flow regime, where we have just an annular shape of water. Here we have the annular flow, and then we have only the dispersed flow. We already talked about these different flow regimes. And here we have subcooled fluid, so no evaporation takes place here before x is 0. And here at the point x star 1, we have only superheated vapor, because here the temperature is higher than the boiling temperature. Yeah, because, and in between, you know that we will have a constant temperature, because the heat that is transferred here is directly used for evaporation, and the heat of the liquid phase will keep constant. You know that you can usually, if you don't have problem with these nucleation, you usually have always 100 degrees Celsius of your cooking water, and that's the same is true here. Yeah, here you have below 100 degree. Here you have 100 degree and phase change. And if no phase change is possible anymore because all liquid has been evaporated, the wall is superheated, and the vapor is superheated. Okay, so how can we show that? So here we have the pipe. Heat is transferred into the pipe. Here we have a mass flow rate. And now let's say we have a constant heat flux. And what happens is that here's the heat transfer coefficient. So with increasing distance in the pipe, we get more and more evaporation here. Yeah. So the heat, the flow through the pipe is constant, but we get more and more evaporation. So this gives us the evaporation here, the boiling stream. And the boiling stream, of course, increases with increasing distance. And also it increases with increasing volume flow rate here, for sure. And it increases additionally with increasing heat flux. Now, I guess this is not very surprising. Higher volume flow rates, higher evaporation, and higher heat flux. And we get higher steam mass flow rates. So you can see this in this diagram a little bit more in detail. Here we have the mass flow rate through the pipe. Here we have the heat flux, and this is a heat transfer coefficient. And in this double logarithmic diagram, you see with increasing heat flux, we come to higher heat transfer coefficients. So this is here the example for evaporation of water at 1 bar as a function of the mass flow rate. So the mass flow rate helps, of course, to increase alpha. Yeah, you remember our Nusselt correlations where we have the Reynolds. Yeah, Nusselt is constant multiplied by Reynolds to the power of m multiplied by Prandtl to the power of n. So in the Reynolds number, there is already this mass flow rate here included, but you see that you can even stronger increase the heat flux by increasing the heat that is transferred coming into the bubbling regimes. Okay, and how does it look like with the temperature coming back to these dry out? So here you see the pipe again and how water is evaporated. And here you see the temperature. So this is a saturation temperature here, this line. Yeah, this is a saturation temperature. First of all, the liquid is subcold, so we have a lower temperature than the saturation temperature. And at this point here, the liquid overcomes the saturation temperature. And at this point where the temperature is higher than the saturation temperature, the first bubbles will appear, the first vapor bubbles. Yeah, so here we have single phase flow. Here we have bubbly flow. if we increase the heat flux further, so here we have even higher heat fluxes, in that case, or let's say, sorry, we don't have higher heat fluxes, the heat flux is constant over the whole pipe, yeah? Sorry for this confusion. We have a constant heat flux over the whole pipe, but more and more water is evaporating. And now you see that first we have we overcome here the saturated temperature. So now evaporation starts, but the temperature keeps constant more or less because we have evaporation. Yeah, this is this range where we have 100 degrees Celsius where the water, for example, is cooking. So constant temperature, all the heat that is fed into the pipe is used for overcoming the latent heat and for evaporating water. Okay, so we come from bubbly flow, slug flow, annular flow, and here annular flow is entrainment. And now suddenly at this point, all the water is evaporated. So we have still a constant heat flux, but there is no water anymore, no latent heat where the heat can be transferred to steam, from water to steam. And what now happens is, because there is no latent heat anymore left for the evaporation, the heat of the wall suddenly increases. And this is our dry out point again. Yeah, the same what we have discussed before on this metal wire. Here we have this now at the pipe, and it's the same situation. Yeah, and here you see that we have this strong dry out. Of course, we still have some convection, so the temperature will change a little bit here. And then at this point, there is no vapor anymore, and we have only an increase in the temperature by radiation and heat transfer to the vapor here. Yeah, here we have only a single phase vapor flow. Okay, so and once again, this is an extremely dangerous situation where the temperature of the pipe, of the wall here suddenly increases because of this dry out. And this is extremely dangerous if the metal pipe is melting here because of the too high temperature. Okay, so take this into account and be careful not to come to the situation, to this dry out point. You always need to have enough water in your cooling system to be sure that all the heat can be transferred. Okay, if you have no further question for the evaporation, I would like to switch over to condensation for the last 15 minutes. Don't worry, it's not so much more because it's a very, very similar process. If we have condensation, you know this from your mirror in the bathroom in the morning after you take a shower, then you will not be able to see you in the mirror anymore because the mirror is cold, and therefore the steam from your shower will condensate at the mirror. And if you look in detail, you see these tiny water droplets from your shower on the mirror. And even here you have a very good heat transfer performance because here you get the latent heat back by the condensation process. And if we have an increased convection for evaporation, if the vapor bubbles are rising, here you have an additional convection by the droplets who are created and who are running down the vertical surface. Yeah, so the drops slide off and wiping the plate here, and with that they increase the heat transfer, and of course they create new fresh surface where more condensation can take place. Okay, so this is because this is the reason why even condensation is a very, very efficient heat transfer process. So how can we describe this in detail? Here you see the film condensation. So vapor comes here and is cooling down at the cooled wall, and then you get a condensate film that runs down, and here you see some condensate droplets. So we distinguish between film condensation, if we have a lot of vapor and liquid, or drop condensation. And here, of course, the surface tension and the contact angle plays a role. We already talked about that interfacial tension in case of partial wetting. So if we have here oil or water mixtures or more or less wettable surfaces, then this has to be taken into account because this condensation process strongly depends on the situation, film condensation or drop condensation. So another important point is that you might have some non-miscible liquids. I already mentioned oil. So very often in industry, you have oily vapors. And in that case, you have to be aware of oil that is condensating with the vapor droplet. So here the vapor is flowing through the cooled wall, because don't forget, if you cool down steam and the steam condensates, then the volume of the steam rapidly drops down. Yeah, a milligram of water has a much lower volume than a milligram of water steam, as you know. And therefore, if you have a condensation here, then you have a strong vapor flow to the surface. And this means that oil droplets are always transported to the surface as well, and they may stick at the wall, and they might isolate your good conducting surface here. Yeah, this might be a problem. Non-miscible liquids, and especially if you have in a condensating situation where you have such a pipe, you might have this mist droplets, and they can condensate at the wall. And this brings us to a very important other phenomena. So it might happen that you have a heat exchanger that you use for condensation, and in your process, you're an engineer now in industry, and in your process, the heat transfer works very well first, and you have a very good condensation, and suddenly no condensation takes place anymore. You have still the same temperature difference, everything is the same, but the condensation breaks down. There's no condensation anymore in your process. And this, of course, is very surprising if something happens like this, if nothing has changed, but suddenly you have a breakdown in your condensation process. And the reason for this might be that you have a kind of non-condensable gases. So what does it mean? I already mentioned you have the condensation film, the condensated film here. So this means due to the condensation and the decrease in volume of steam, you have a lower pressure at this condensation site than in the bulk flow. So this is here the overall pressure, and the pressure of the steam decreases here due to the volume decrease. Yeah, I guess this is not very surprising. But what does it mean? This means if you have another gas in the system, like nitrogen, then the nitrogen will also flow to the left-hand side, to the condensating plate, but the nitrogen will come if the partial pressure of the steam decreases, the partial pressure of nitrogen increases. So in other words, you might get higher pressures, higher partial pressures, and therefore higher concentrations of so-called non-condensable gases. And these non-condensable gases here, of course, might create another kind of isolating layer. Yeah, here you see the temperatures. This is the temperature at the wall. We have here the temperature at the film. And this is the temperature in the vapor and in the gas. So the temperature decreases here, of course, as well, because we have the condensation here. So here the temperature decreases, and this is a temperature in the film just by conduction. But this temperature difference here depends, of course, on the conduction through these film. And if you have non-condensable gases, let's have a look on that, then it might happen that this gradient here gets much steeper due to these condensation, due to these non-condensable gases. So what can you do about non-condensable gases? Yeah, it sounds strange, but unfortunately it's true. You have to open your heat exchanger time by time to release some vapor, and with the vapor you release the non-condensable gases. Of course, you lost energy if you do that because you release steam, but it's better to release some energy by releasing steam than creating a barrier against heat transfer by non-condensable gases. Yeah, this might be sometimes a problem in heat transfer processes. Good, so we have almost done just the correlation that helps us to calculate the condensation. Here we need one more additional dimensionless number that gives us the ratios in these condensation processes, the so-called Jacob number. And this Jacob number, let's have a look how it looks like. Here, this comes from the dimensional analysis. We don't want to go too much into details here, but the Jacob number takes into account the evaporation and condensation latent heat. Yeah, here we have the latent heat for evaporation, and this is taken into account, and it gives us a ratio of the conductive heat transfer here by the latent heat. Yeah, this is the ratio. This gives us a Jacob number. And now we can create a Nusselt number that is a function of Prandtl and Jacob and the Reynolds number. And this is an empirical correlation here that helps us to get an idea of the heat transfer performance for a condensation process. Okay, and here we have once again this inert gas situation that I have already mentioned. We have the partial pressure of our steam and the partial pressure if we have inert gas. And here you see for without inert gas, we have all the same pressure, and we have a nice conduction here through the liquid film. And if we have an inert gas, then we have a strong decrease in the partial pressure here in the film, where the inert gas is already present. And this means that we have also in the inert gas a strong drop in temperature due to this isolation inert gas layer. And this means we have much less temperature difference left here for evaporation. This was a problem of the inert gas. So in the last 5 minutes, I would like to show you a nice idea that is used for very efficient heat transfer by make use of condensation and evaporation. And this is a so-called heat pipe. And how does it work? A heat pipe is using evaporation and condensation in a very small space. And this works like this. So we have here an evaporation area, and this is a condensation area. And we only have a very tiny space here in between. What happens now is here we have evaporation. We use the latent heat for evaporation. So we can feed a lot of Q here, a lot of heat. Then the vapor is going up. And here we have the cooling side. So here we have a very strong condensation. This is a condensator. So by condensation, the volume of the steam is strongly decreasing here. So this is why we suck the steam from the lower part to the upper part. So we will have a very strong convection here from the lower part to the upper part. Evaporation, condensation. And how do we bring now the liquid phase back, the condensated phase? We do this liquid return by a material here that works like in a candle, the wicking material. Yeah? Wicking is the Docht, and this Docht, diese Dochtwirkung, this wicking material helps to suck the liquid down here, and so that it can evaporate here again. And this helps us to bring a lot of heat from the left-hand side to the right-hand side, because we have a strong heat transfer, and we can use the latent heat for evaporation and condensation. And this is much more efficient than just using convection. Yeah, you might know that the latent heat is 1,000 times higher than the heat that can be transferred just by conduction. So you can save 1,000 times the volume flow rate here by using these heat pipe systems. And it looks like a strange system, but indeed this system is used very often, and especially in very modern components. And here you see, for example, a heat pipe for cooling a microprocessor. And here you see the fins that are bringing away the heat, and we have the heat pipe here inside of this material. So this is a nice, very modern heat pipe used for cooling down microprocessors in a very tiny space, combining evaporation and condensation on a very small space. So that's all for today. Do you have any questions left? We still have a few minutes. Do you have any question related to this lecture today?
What's the example of a wicking material that's being used in the industry?
Yeah, this is you can use this from. There are some steel wools, for example, because steel wool is more resistant than just wicking material here from a candle. Yeah? but you need a material that sucks very strongly the liquid, and of course it depends on the liquid that you are using. Usually you use some refrigerants for this kind of application as well, not only water. But steel wool works as well. So that it needs to be a material that sucks strongly the liquid phase and transport this downward again.
Okay.
Any other questions? Okay, then thank you so much for your attention today. I know it's much harder for you to follow me online, and even for me, it's not this pleasant than see you and discuss with you in the lecture room. But I guess due to the Corona problems, it might be a good idea to have this today online. I hope that we will see us again in presence in the lecture room next week. Actually, we will talk about next week about these mixing and mass transfer and stir tank reactors, or maybe we first do the design and scale up. I cannot say this right now, depending on if we can go to the lecture room again or not. So if we are online, then probably we will first talk about mixing, mass transfer and stir tanks. And if we are in present, we will use this topic, design and scale up of reactors. Now we will see. Okay, so thank you so much for today, for your attention and for your questions. This was very pleasant that you asked some questions in between. And I hope that you all keep healthy. And yeah, please enjoy the rest of the day and the week. And hopefully we will see us again in presence next week. Thank you so much, and bye-bye.
Thank you. Bye-bye.
Bye-bye.
Bye-bye. Bye-bye.
Thank you.